Hello, everyone, and welcome to ABC Stone. I'm Lyndsey Belle Tyler, and I am the creative director around here, and I'm so happy to see all of you at the standing room only inaugural event at our new event space. It's incredible. Thank you all for being here. As you can imagine, kicking off what will be 4 events a year that are not only educational but entertaining in this space with a 36-foot stone beam is not an easy feat, but our fearless leader, Jonathan Tibbett, saw it last summer at an exhibition in London and said, come hell or high water, we are getting this beam here and we are going to educate people about structural stone. And we all said, okay. And then we had to make it happen. So I called Rosalie and Anne from the Architectural League, and I said, come hell or high water, I need to bring a 36-foot stone beam from London to New York, and I'd love your help getting people to come see it. And luckily, they obliged. So here we are. We could not be here at a more imperative time. With the climate crisis the way it is, I feel like the people in this room can singularly make a change and can educate and can make sure that everybody understands what is possible and what we have to stop doing. So thank you all for being open, and thank you all for understanding why we're here. I am so happy to introduce Rosalie Genevro, the Executive Director of the Architectural League of New York.
Thank you, Lyndsey. Lyndsey is so modest. I mean, we are so pleased to be here and to be able to join with ABC to present not only the equanimity beam, but the presentations and the fascinating questions and discussion that you're going to hear tonight. So grateful to Jonathan, to Lyndsey, to Tina, for everybody at ABC for making this all possible and for bringing this to our attention. From the League's point of view, this fit in perfectly to a series that we began in February with an introductory. The series is called From Field to Form, and we began it with a program in February that was catalyzed by a remarkable book called Manual of Biogenic House Sections by LTL Architects. And at that introductory program in February, we also had presentations by Lola Ben Alone of Columbia and Mei-Ling Loco of Yale and Jean-Sarah Ruth of Parsons School of Design. We're continuing this series. So this is program number 2. Program number 3 will be on Friday, April 28th, and it's titled From Field to Form, Making with Earth. And that one is organized by Lola Ben Alone and the Natural Materials Lab at Columbia. More information about that will be available in a couple of weeks on our website. But the whole series is about exploring the potential of natural materials, both earth-based and plant-based, not only in terms of their environmental impacts, which are much reduced from other materials, but also in terms of what they offer for new opportunities in form making. The only other thing I would like to say is that I'd like to welcome and turn the program over to Nat Oppenheimer. Nat's a structural engineer and runs Silman, one of the premier engineering practices in New York and around the country. Nat also teaches at Princeton, and he's also the treasurer of the board of the Architectural League, and he will introduce our speakers tonight and then moderate the discussion. So over to Nat.
So Steve Webb has become a colleague and a friend the last couple of years because I've been fortunate enough to be the engineer of record on a couple of projects that he put his amazing structures into. So I very much am looking forward to this. Steve worked at Whitby Bird and Sinclair Knight Merz and Santiago Calatrava before he started his own firm. And he worked at those firms on prestigious projects, including the Wembley Arena and Turning Torso in Sweden. As many of you know, Steve has always been interested in combining imagination with technical rigor, which many of you in this room I know appreciate, to create artful and inventive structural designs. And since founding his company, he's led a number of prestigious and multi-award winning projects, including 15 Clerkenwell Close, the Cantor Center of Excellence for the Anna Freud Center, and the Hoover Building. But more importantly, tonight, he's pioneered the practice's approach to innovation and sustainability, encouraging the use of non-conventional materials from cast iron to cork and from inflatable to stone to design low-carbon and environmentally conscious structures. And in 2020, Steve was awarded the Milne Medal from IAPSE, which is incredibly prestigious, and for continuously challenging and redefining what is considered possible in structural design. The awesome part of that is that it was during COVID, so it's on YouTube if you want to watch it. Steve also regularly lectures at universities and events, and he's taught at the AA, RCA, and the Bartlett, and has written for a number of industry magazines. So thank you, Steve, for coming over the pond to visit. Pierre Bidaud has been a stonemason for 30 years. He left France for England in 1998 and developed an interest in design and contemporary architecture and worked on new stone projects in collaborations with designers. In 2009, a meeting with a structural engineer, which I assume was Steve, although who knows, reinforced his confidence in stone as a supporting element in contemporary building, and he embarked upon research to develop a new construction method, combining stone with steel and high-performance resins to create stone on steroids, essentially. And for 10 years, he's worked at the Stonemason Company with a growing team of stone enthusiasts, designing and developing stone staircases and structures to create works that appear to defy gravity whilst also being load-bearing. He is a strong advocate for pivoting of the stone industry towards the manufacturing of pre-assembled stone elements, and he believes a new generation of carbon-neutral hybrid construction should be proposed to architects, engineers, and clients, and that stone should again be considered as a commodity and not a luxury, and that's hopefully what we can get into tonight. I'm sure we will. And finally, Jonah Wurzer-Kinsler, who's going to join us for the conversation after the presentation, is a partner at Frankenstatter in Germany's largest producer of limestone and environmental leader in the stone industry. So as I turn it over to him, I think what struck me tonight as I think about this is it brings back a lot of memories. I think Steve has talked about before, thinking about stone as where we were with CLT in the 90s and now where we are. So have an open mind as you watch all this. For me, it brings back incredible memories of being in Finland for conferences in 1999, 2001 on structural glass, when sort of people thought there was no way, and now we think of it all the time in that way. So, and again, it came from Europe, of course, over to the States. So we'll have that conversation after.
Thanks very much. I think Nat is reading from our website that there's nothing more painful than having your own website read back to you. So you probably don't often hear engineers talking about morality. I think quite often we're facilitators for other people's visions, but I'm afraid I'm a little more opinionated than that. So we're going to talk about the social context of building design and engineering. People rather like engineers who design buildings that don't fall down. So this is the primary driver for hiring an engineer to design anything, is you don't want your buildings to fall over. You might get an engineer because you want to be more economical with the material, make your building a bit more affordable. An emancipated engineer will combine art and physics to make structures really beautiful and lift your building. And after all, architecture is structure, or structure is architecture. But we try and think a bit further forward than that. What kind of employment are we creating when we're building buildings? Are we creating work for machines, or are we creating work for people? What kind of work are we creating? What kind of lives are we engendering by designing buildings the way that we design them? In the 1950s, after the Second World War, there was a shortage of coal generally, and manpower was cheap and material was very expensive. And so the kind of structure that this engendered from, in this case, Luigi Nervi or Felix Candela in South America, Eladio Dieste in Uruguay, structures that are very highly designed, spend a lot of time designing them, a lot of time building formwork to minimize the amount of material. And we were kind of interested to think about the impact that income tax has on this equation. So you tax employment and you tax labor and design. You don't really tax material and machines. So in our society, we tend to over-rationalize, minimize design, minimize carpentry, formwork, and just chuck lots of concrete and steel at problems. CNC, everybody loves CNC. It's the future. Robots are going to make our lives absolutely amazing, but they're probably not going to make the lives of the people who used to do those jobs amazing. There'll be a lot of people languishing on universal income as a consequence. So how do we make decisions in the way we build that are good for society? The construction industry at the moment is deeply steeped in the fossil fuel era. All of the materials we use, steel, glass, concrete, brick, they all come from coal-fired processes, and they use unimaginable amounts of energy compared to any amount of energy that was used before. But immediately prior to this period is what we in the UK call Tudor, but this style of building is repeated all over the world. Timber construction, very, very lightweight, using a tiny fraction of the amount of energy that was used on subsequent buildings. So even in this case, the building just to the right of here, you can see the bricks, they burned lots of coal to make that building. They didn't burn any coal at all to make this. So when we're practicing, we design, in our practice, lots of steel and concrete buildings all the time, but we try to offer alternatives. So we try to offer alternatives that we think are socially better than the ones that we normally use. And people say, how do you evaluate this? How can you understand what materials have high carbon or what materials don't have high carbon? And there are lots of spreadsheets and websites to work this kind of thing out. But for me, it's very simple. If there's fire in the process, then clearly it's a high carbon material. If there isn't fire in the process, then it isn't. So we're pushing generally to build more with timber and more with stone. So what is the impact? So the social, the biggest social challenge of our time is global warming. What are the impacts of these different materials duty for duty? So this is a 2 meter, I've got to convert to imperial 7 feet. Sorry, 7 feet, a 5 bushel car. These are all sections that are capable of supporting that car over that gap. So this is an 8-inch by 4-inch piece of timber, narrower pieces of hardwood, 2.1 millimeters of steel, 28 millimeters of concrete, 22 millimeters of post-tension stone, like the thing hanging over your heads. Thank you for whatever modeling you're doing. Yeah. These are the sections that have the same stiffness. These are the carbon footprints per meter of those beams. So it's about 50 pounds of CO2 per meter for the tiny slither of steel, 14 for the concrete, 5 for the timber, and minus 16 if you consider the sequestered carbon in the timber, only 1.5 for the stone. And the reason is the stone is very strong. It comes straight out of the ground and it's already made. We, in our incredible construction industry, take 15,000 PSI limestone, we crush it up, we get a lot of gas, we burn it, not only releasing the carbon from the gas, but releasing the carbon from the chemical process of making cement. We get fresh water and sharp sand, both of which are in short supply. We put up formwork, reinforcement, backpropping, vibration, releasing agent. 28 days later, we have a piece of concrete with a strength of 4,000 PSI. So we've thrown all these industrial processes at this piece of material, and we've rendered it with 1/5 of the strength that it had in the first place, which to me at least seems a little perverse. There are probably historical reasons for that. People question, is stone sustainable? It's going to run out. Somebody asked me what's going to happen when all the stone runs out. So we're going to be floating around the sun in office buildings and the earth will be completely consumed. Actually, impossible. 7 billion people having a chunk of stone this big is a 40 kilometer by 40 kilometer by 20 meter deep quarry. So the earth's crust has unimaginable infinite volumes of stone. And if you ever got close to exhausting the stone, a lot of new stone would come bubbling up out of the ground in its place almost immediately. So in some ways, we're harvesting geothermal energy to make a building material. The default solution to decarbonization of building is timber, and we were interested in land use. So the UK, obviously, we have very little land, and we like to build. Where are we going to grow all these trees? So this is a tree, has about 1.5 cubic yards of material with God knows what, 7.5 newtons per millimeter square is pounds per. Maybe that can help. Maybe he's bilingual in the units, but a small quantity of a very weak material over a 25-year period. So the tree takes a long time. Underneath the tree, 500 cubic meters of 150 newton material, much stronger, in about 3 months. And you can see this is the Esteyade quarry in the south of France. That quarrying is going to get you a lot more material than growing a tree on the surface, acre for acre. Stone is, as I said, much stronger than concrete compression. It's also stronger in tension, and it's also stiffer. So when concrete sets, it's got a lot of water inside. The water evaporates, and when you compress the concrete, you expel the water, so it has long-term shrinkage and creep behaviors that stone doesn't have. And because stone's stronger in tension, it doesn't need as many stirrups, links, and other kinds of reinforcement. So it's It's by far a superior material to concrete. Like,
Voilà, vous pouvez m'écouter maintenant. Donc, je suis très content d'avoir cette audience ici à New York. You can translate, Steve?
no.
No? Okay. So, sorry. I thought it was a well-educated audience. I was mistaken. I will have to revert to English. And thank you, Steve, for giving me the
It
austerity.
hasn't worked out. I'm the boring one and he's the funny one.
And he's the engineer. I'm the stonemason. So kindly, Steve decided to give me the austerity chapter, which is going to make you. I'm going to try to make it as light as possible. Next slide, please. So this handsome French architect, is Fernand Pouillon. In 1950s in France, in fact, straight after the war, 1945, France was on its knees. Most of the steel, most of the concrete has been used to reinforce the Atlantic coast. Our coal furnace were just not working at all. If you wanted to bring some steel from Marseille to Paris, it could take you 2 weeks because the trains were not working anymore, bridges had been blown. And to reconstruct France and the affordable housing, you need a material that you could get quickly and cheaply. And Fernand Pouillon decided to come with the idea of rebuilding France with something we have a lot, which is not genius, but stone. Now you are going to do the conversion because I'm the stonemason, I don't do numbers. In 1950s, the French government commissioned a study on the use of energy and see how we could build as quickly as possible. And for 1 cubic meters of concrete, you needed more or less 225 kilo of coal.
500 pounds.
Yes. And to do exactly the same for the cubic meter of stone, you just needed 10 kilo. So quite a big difference in the use of the material. So the French government, with of course some of the money of the Marshall Plan from America, was able to develop a new industry, a new stone industry based on a heavy mechanized quarry. Those quarry were going to each quarry, for example, if you're an architect building in Bordeaux or in Paris, you would have used the module that was available in that quarry. You were making the quarry work as much as possible. So the module was going to be different from the east to the west, to the north and south. Thank you. And Fernand Pouillon built those affordable housing, not Fernand Pouillon only, but many other French architects all over France, as I say, from 1950 to 1970. And it really, when we said it was the austerity, it's in England in the last 13 years, we had an austerity economy. And in fact, when you look at the two conditions, 1950s and now in England, you've got this age where energy is become more and more expensive, and the labor force a lot less affordable. And sorry, if you can go one back, please. Thank you. You can go forward and back. Jesus, fantastic. So this is a 60-meter tower built in solid stone in France, in Algiers, in 1956. There is something about it on one of the placards here. And except the concrete slab, all is made of roughly cut stone from the quarry. So straight from the quarry to the building site. Thank you. And between these two pictures, you've got more or less 70 years, but you've got exactly the same philosophy of using stone as quickly as possible and as efficiently as possible. So your keen architect eyes would have spotted that this height is just made in 3 pieces of stone. So the stones are 1 square meter, so a lot of feet square. So they are a lot easier to fit than your small blocks of stone. And these buildings are in Switzerland, built last year, were very much the same philosophy of the 1950s France way of building. Okay.
One step at a time. We're full of...
Because one step and we do staircase.
So when Pierre and I met, Pierre was selling traditional stone staircases, and this is quite a traditional stone staircase. But these staircases are typical all over Italy and Europe, and probably here as well. One stone sits on top of the stone underneath. We call them cantilever stairs. They don't actually cantilever. The load trickles from tread to tread, and because the treads are fixed to the wall in the background, then they stand up. So we started to design those kinds of staircases, but Pierre could only sell flights of stairs to people who had a wall next to the stair. So we began to experiment with how we could design free-spanning stairs. So this is an early prototype of a cable stressed stone beam, 2 inches deep, 10 foot long, 2 half-inch cables running through there with 5 tons of pre-stress. The cables curve so that when they're stressed, they lift the weight of the stone. They push the stones together end on end, and we were better at designing stone beams than taking photographs, unfortunately, and now that thing is in the skip.
We didn't have the budget.
But we worked through and we started designing, first of all, short, straight spans of staircases, then slightly curved helical spans, and then big helixes. And it's a very succinct and simple solution. Each tread is an individual stone. The cables go through the middle and jam them together, and we're able to make these structures. We did some prototyping and screwed it up, and eventually we figured it out. This is Pierre's
torture chamber for a staircase.
Torture chamber for the staircase, so the blue things are full of water. And this was the first a really big helical stair that we designed. Again, you can see that it's shallow. The kind of typical solution to this is to build a concrete stair or a steel stair and overclad it in stone. But you can imagine, how many additional activities are involved in doing that and how much additional cutting. So I'm hesitating because I think we're out of order, aren't we?
No, it's still good. It's still good. Well, I'm not listening to you anymore, but I it seems like I listen, but no. Just
you talk now.
Okay. That's not mine. That's yours still. Yeah, still yours.
Okay, so
don't wake me up.
So we designed all these very crazy staircases. This one has a single cable through the middle, much more zoomorphological than the other ones. But we didn't really do this to serve the high-end property market of staircases, although it was an amazing testing ground because there's a lot of money in this and we're able to experiment. People want audacious structures, but what we really want to do is build buildings. I wasn't out of order, sorry.
Yeah, it's okay. I still know the building, so that's fine. So in 2016, you both sent us commission to build a stone staircase made of solid stone blocks. It was going to be a brick building, but Amin decided to look into a more efficient way of building with using sustainable material like stone. And Steve and his team, the next one, invented. At the time, I was naive. I thought you added a bit.
The load-bearing building. We did.
The very first stone building in the world. Yes, so the system was an exoskeleton made of a succession of columns and beam who were attached by a connection box to the concrete floor. Do you want to explain the way it was built with the concrete floor, Steve?
So if the subcontractor was the same person building the stone as building the concrete, they would coordinate themselves and they would share hook time on the crane and it would be really easy. But they're obviously not. You have stonemasons and concrete contractors. So in this case, we built the building concrete frame on the temporary propping. We left the temporary propping in and then we built the stone afterwards and then took the temporary propping out at the end so that you can separate the two activities and reduce conflicts on site.
So working on the same philosophy of Fernand Pouillon, Amin Taha decided to go for a very honest and raw finish to the stone. So again, to simplify the finishes and to simplify and make the stone a lot more affordable, he decided to go for how the stone gets out of the quarry. So split or just the raw crust of stone. And I think on the next slide we can see it. Maybe the next one. Yeah. And you can see here that he decided to leave some what we call a sawn face, which has been cut by our big saws. Again, this exercise was about economy of energy and efficiency. I think the next one. Thanks. Okay, that's yours now.
So what else can we make? So the stairs are really complicated and very difficult to analyze, but actually simple beams and columns, very easy to analyze, and these are building components that we can use anywhere. So we make standardized rectangular blocks. We drill a hole through the middle, we put a cable through the hole, we have a cuff and wedges to hold the cable at tension, we put it through with a jack, and we can make a beam. We can do the same thing with stone to make columns. We can use stone plates and put cables in between and make slabs. So you can make very simple, and it's actually very easy, very, very simple building components with stone. We have a R&D program in our company with an annual budget of about $1.50, and
it's been increased to $2 since last week.
We hit a big time. So we've been doing lots of with Pierre and his team improvising tests. And actually, Wendell in the middle is the head of special structures at University College London. But we're testing the beams for strength. We were really concerned that if we make a limestone building and it has a fire, if you burn limestone, you get cement, referencing the earlier slide. So we're worried if we have a fire in a limestone building, we're going to end up with a nice heap of cement afterwards. This was a fire test of a 600 by 300 beam spanning 7 meters, 7 yards, 20-something feet, with two 10-ton loads on it. Actually, because concrete has water in it, when the water reaches boiling point, it turns to steam and it explosively spalls the concrete, exposes the rebar melts and the beam falls down. You didn't get that with stone. It just sat there passively, and we got 3 hours of fire resistance from this beam. So in a 1,000-degree furnace, so very effective. This is not the first exhibition we've done. We did one in the building centre in London called the New Stone Age, and we were talking to a commercial developer in London about what they would need in terms of building components, and they're building trading floors, and they're saying they want 12-meter column-free spans, which is I don't know what. So when you walk into a trading office, there's loads of meeting rooms and desks and all that kind of stuff. I don't know why they need column-free. Column-free is really bad for the environment. It takes a lot of energy. I think they clear the desks away and go roller skating at weekends or something. But anyway, this is a 12-meter span, 450, 1.5 foot deep, 8 inches wide, 2 cables, 2 half-inch cables running through there, and a 3-inch stone slab on top. So it's kind of useful, very simple building component. This one you have behind you, so I don't need to point at that one because it's up there, but here we're trying to invoke a concrete, a standard concrete T-section. What we have in the ends is recycled granite, so this is recovered from a Pomo building. Granite's much stronger than limestone, so we're using the granite in the points of high stress. In between is Portland roach bed. So Portland is quite an expensive stone in the UK, but nobody wants the roach bed because it's kind of ugly and it's not the right color. So we got.
Whoa! What do you mean ugly?
Okay,
that's limestone.
Beautiful, but people can't.
Thank you. Thank you. Don't be judgmental like that.
Stop heckling.
It's not ugly.
So you have the 2 cables. The cables curve upwards to a crest in the middle and down towards the end. So they're kind of tenons on the top of this. And yeah, it's supported on a timber trestle. So in both instances, we're making a point about the combination of timber and stone, and actually the stone being quite light and the timber being quite strong.
Yes. So 2 years ago, we were commissioned a 3,000 square meters private house in England, and the aim was to be as sustainable as possible. The client had very much in mind to use as little possible concrete, and 2 materials came straight away. 2 materials that could be easily scalable in their use, which was CLT and stone. Again, using the principle of large pattern stone module to speed up the process of fitting, but also including what we've been developing for the last 10 years, which are just all those elements through the transparent visualization is pre-stress, so done off-site in our workshop, stone beams. Here you can see one of our assembly line where we produce such beams. What we are trying to do is to speed up the process of fitting of those beams, and to very much like the precast concrete industry. Even architect in France now sell stone as natural concrete, just to make it a bit more sexier. The fact that a lot more finishes can be applied to stone. You've got split, you've got just left raw from the saw. But the fact that we can produce pre-assembled element means that on site the main contractor is less reluctant, because if you start to bring 30 stonemason coming to fix one stone at a time, it's problematic for the logistic and strategy of building. Here you see some of the stone floor, again with some of our cables that are used here. And here you can see we've got a large area. I don't know how much in it fit. That's why I'm describing it as a large area. In stone, you can see the succession of stone slab. We've been pre-tensioned, and here the whole floor. I do believe it's the first one in the world, but the first floor, this floor is all in pre-stressed stone. Yeah, go on.
So we're looking at other ideas and ways of using stone. In European culture, stone tends to be funicular, so we tend to use it always in compression, and it's never really used in tension. But in Indian culture and other Asian cultures, it's much more common to use it in bending and actually use the stone in tension, which we found very interesting. So we were asked to do an exhibit for the Victoria and Albert Museum in London to look at an engineering principle, and we came up with this idea. So this is a 10-foot by 10-foot slab. It's supported around the edges on these steel stalks. It spans from one side to the other. The little diamond shapes are washers that hold the stones vertically next to each other. And you can imagine that this stone in the corner, because it's supported on 3 points, is stable on its fourth corner. The next stone is built in next to it. It's fixed on those 2 points, and it's fixed to the previous stone. The next one on those 2 points fixed to the previous stone. So you can build up this reciprocating stone structure. So we're able to span 3 meters in 40 millimeters of unreinforced stone for a full domestic load, which is very, very effective. We're thinking this can be developed for a standardized building system. So columns, post-tension beams, slabs in between made out of that reciprocating floor plate. And you can see there's a kind of typology emerging from that. But we, like all materials, when they built the first iron bridge in the UK, it's a wrought iron structure, they only understood carpentry. And so all the detailing on that bridge, and it's like 300 years old, wedges and mortise and tenon joints, because the people could only see wood, even though they were designing with steel at the time. When they first started building in concrete, they were emulating stone buildings. CLT kind of emulates concrete in some way, but eventually those materials find their own typology. And we, similarly, are stuck with concrete in our heads. So whenever we're designing stone structures, we're producing things that look like concrete because we're inflected with that technology. But I think this, maybe it's more like a steel typology. Maybe we're making stone columns and beams that get bolted together more like a steel structure. So this is a material in want of a typology, and it's a kind of open field. We don't know what it's.
But it's also to disturb as less as possible the general contractor way of building. If you tell them that it's only a switching of material with easy connection, then they are a lot more open. It's less traumatic for the general contractors than suddenly changing all his gear, which understandably, yes, costs money. But so we just propose to switch from a precast structure made of concrete to a pre-stress off-site construction of stone members.
So I don't think I've made this point clearly enough, but this, the beam above your heads, if that was a steel and hollow rib beam, it would have 15 times more carbon footprint. So this solution or this kind of framing would be very, very powerful in decarbonizing construction. And
a bit, we sometimes forget that one of the first way that concrete was used was for warehousing and very cheap offices. Especially, definitely in France in the 1900s, when concrete was starting to be used, people were using it as a material for cheaply and quickly built so warehousing. And recently in the UK, with some new not regulation, but a push by the government to build more sustainably. Some urban logistic hub have been asked to go as green as possible. And here, what we have is urban logistic hub, all made of stone. As you can see, the size is quite impressive, and it will be a complete stone frame with CLT infill.
So then I was in Mallorca. So Mallorca, they're starting. And Mallorca is full of stone, and they're starting to rediscover their architectonic roots and rebuild or build social housing in solid stone. So this is new social housing. Everything is stone vaults, stone walls, and the reason is they're obviously sat over a great big pile of stone. When we try and decarbonize construction in Britain, we tend to use CLT, cross-laminated timber, but that's a technology that we're importing from Switzerland and Austria and Nordic countries where they have a lot of trees. We don't have that many trees either. And the guy here was saying there are 7,000 spoken languages in the world. There should be 7,000 architectural languages, and they should all derive from their local surroundings. So I was kind of thinking, we're importing solutions. What in Britain is our language? So we have been designing a number of buildings with mixing high density materials for thermal mass in the building with timber. So here we have a timber frame, quite a big timber frame building, timber beams and thin concrete slabs. And the reason is that if you have that bit of thermal mass above the ceiling of the space, you don't need to have air conditioning that cools, open at night and cool the space. The timber and the concrete is fixed together compositely, so when the timber beams flex, they use the concrete to resist the flexure, and you end up with this exposed concrete and timber soffit. So I'm thinking the next obvious solution to this is to get stone and timber combination. So this is a concept sketch. We do every size of project in our practice. We do little back extensions and we do big office buildings. So we're able to have an idea, find a victim, test it on a small project first. So this victim's back extension was the guinea pig for composite hybrid timber and stone. So we have timber joists, stone plates in between, a post-tension stone beam spanning across the back of the building, timber beams holding up the back of the old.
The sketch, the engineer sketch as well as a maker. The engineer sketch allow them as well to hide mistakes because it's on scribbly bits. So after that, they just scribble around and say, "Oh, just do this connection here." Okay, and you look at the drawing and you say, "Oh, it's beautiful drawing. That's can only work." And then when you go back to the workshop and you look with the guy, you say, "What have they done?" But it's still a beautiful drawing, Steve.
Yeah, I take back what I said about CNC. Sometimes it's a really nice job to deal with craftsmen. So this is this one built, and these are my terrible iPhone shots of a site in construction. But post-tension beam for the long span, timber post holding the post-tension stone up, timber beams, stone in between. And, for us, where we have just a little bit of stone and a little bit of timber, this kind of typology is great. And actually, it's acoustically quite good, and it's good in fire, and it means we don't have to have air conditioning, and it's quite beautiful to look at. And we find a typology that responds to our local.
Also, as for quarry owners and stonemason, it allow you as well to use some stone that will not be used for flooring, for example, and can be used not for this new use. And by finding new ways of using the whole range of stone in a quarry, you make stone a lot more affordable than it is.
This is a proposal that it's being developed at the moment for a hybrid residential tower. So it's using the kind of henge type facade load-bearing structure with timber floors on the inside. So it's timber and stone in combination on a really big scale. The stone deals with a lot of fire problems and is also the facade element. And this kind of building, if you consider sequestration of carbon, this is a carbon negative building. So suddenly, building goes from being the primary cause of global warming to actually part of the solution.
That's it.
Thank you. I think we should just stand because that's like a comedy routine you had going there. That was excellent. And I have to say, Steve and Pierre sent me their slide deck. It was like 85 slides, and I figured, no problem, I have nothing to do tonight because it'll take too long. But of course, you did it perfectly. So now I have to moderate. I really appreciate both of you coming and giving this presentation together, because I think what's so important about this discussion and about the work you're doing and about the way we think about this, and we don't think about it often enough in the world we inhabit, where everything is bifurcated into designer and builder and everything else, is how important it is for these collaborations to make this a success. So without further ado, I do want to invite Jonah into the conversation, because I think a big part of this work is not only the design and the fabrication of the work, but the material. And I think, Steve, you put up an incredibly compelling slide about the carbon footprint and about the amount of stone on Earth, but from the quarry, in terms of, somebody who runs a quarry that really thinks hard about sustainability and so on. Take it away. What can you tell us?
So obviously we need to take stone out of the ground, and we're using theoretically, it's a non-renewable resource. The stone is 150 million years old. It's going to take a while for that to come back. So as we take it out of the ground, we need to make sure that we're using it in a very responsible way. And you need stone for a lot of things. You need stone for, road construction. So we're using all our waste. We have no waste. We want to use everything down to the last bit, the last crumb. So we're trying to always think of new ways how we can create more value out of what we're taking out of the ground. So as we're cutting stone, what the cutoffs, that's going to be crushed up, used for aggregate, could be used for fertilizers. Carbon, it's basically calcium carbonate is what the stone is made out of, so we can use it for fertilizers for farming areas. As we move the quarry, it also creates biotopes. So the areas that we have in the quarry, right now we actually have a Eurasian owl eagle that was thought to be extinct, but because the quarry areas is creating cracks, we're finding all these wildlife returning to these areas and really thriving in these areas, in these quarries that we have. And then in other cases, what we can do, we have waste and we have garbage. Where are we going to put that garbage? What are we going to do with it? So we can actually deposit that in the ground, reclaim that and renaturalize that area in that quarry, and we're bringing that back to nature. So as we move, we're not leaving vast areas open of quarry land that is maybe looking at unsightly, but we're going to fill that up. It's going to be renaturalized. You're going to walk on top of it. You're not even going to know that that there was a quarry there. So that's one thing from the quarry is what we're doing, and what we're very focused on is being sustainable in that manner. So,
and we are going to ask for questions at some point soon, so please come forward with some if you have them. I think one of the things that struck me, and as I said at the beginning before you started, I think the analogy that's in my head is early days of structural glass and the collaboration between the glass fabricators, between the engineers, and it was not codified. And that was part of the fun of the whole thing, right? And you guys have been doing amazing work playing in the lab and building amazing structures, but it's been very much because you trust each other and you've been able to fail and then succeed. What as you look at these buildings now, as you're getting into you're already in the market, but as you're getting into the occupied building arena, what are you seeing in terms of code officials and so on? As we talk, I don't want to make it just about engineering, but as we talk about scaling this up beyond just an academic study or a stair for a private residence, what are you seeing in terms of acceptance, not just for fire, but just redundancy and so on? Are you finding no problem, or are they accepting it based on testing, or how's it going?
Yeah, I think there are very few. There are codes for stone for facade use and for decorative use, and there are odd codes around in different countries, but not very comprehensive codification, and not really very good codification of supply of stone. So you can't go and say, I want a 30 Newton stone and get guarantee from the quarry that the stone is going to be there. So we're always having to invent methods of calculation and ways of demonstrating that what we're doing is safe, and ways of assessing the stone's the stone's inherent properties before we use it. But actually, it's quite similar to some uses of concrete, post-tension concrete, to other masonry codes. So we find codes that are analogous to stone, and we tend to shadow or follow them. And what we can't do, we demonstrate by testing. So the Eurocodes all have testing routes, so you can use testing as a way through the codification. The UK has quite a permissive regulatory environment. The only building control thing for structure is your building shouldn't fall down, and you can demonstrate that it's not going to fall down in whatever way you want, or you can follow all these regulations. So we work in an environment that's not massively regulated. But we find that people are far more concerned about timber. I'm very, very nervous about timber because of fire and durability. They're not so, and I think people's concerns about structure tends to be, we're not in an earthquake zone, so I think also it's a slightly more benign environment. But yeah, we found stone appears to be quite traditional, even though we're using it in this way, and it doesn't excite the checking authorities in the way that other materials do.
Yes, the question is. One of the question, of course, is scalability. Can you scale these things? So the first thing is quarries. Can quarries handle suddenly a triple, quadruple of the production of stone? They can. They just don't do it at the moment because most of what they ask to them is just cladding or flooring. But if suddenly there's register an interest of load-bearing stonemasonry, we've got few examples in the last 20 years where quarry suddenly, especially quarry where they have a stone which is not fashionable anymore, or was as my colleague here said, are ugly. You just discover that suddenly there is a lot more interest. The quarry that was used for the Plan des Ouates just next year was a quarry which 20 years ago would have closed. Because you couldn't do flooring, you couldn't do anything with it that was of its time. And now they just got a order of 2,000 cubic meters. They've got another 4,000 to produce this year, and you can see this shift happening. So scalable, it's possible. And again, if you work with the general contractor just to change as little as possible their habit, then I don't see it as a problem.
I think one more thing to add to it, because this beam may look expensive, but if this can be done in really an industrialized process, and you can repeat that, a lot of the stuff that we have expenses in stone is because every single piece of stone on a facade is often a single piece of stone on the facade. You'll have a left end, or all the sizes are different, so we're challenging the economies of scale here. And what we have here is we can really make this an industrialized process, and then we can shoot it out and really gain from that economy scales to drive the cost down.
Yeah, actually, building on that, there's a beautiful sculpture in Boston, the Collier Memorial that Halle Yoon designed. And there's, not to get too engineering on the whole thing, but there's a whole backstory that's pretty fascinating about the engineering of that arch and whether you put pins in or not. I won't go into it here. But part of what came out of that story, which was fascinating to me, was just how precise the stone had to be quarried in order to achieve the arching that was aspirational there, or it was achieved there. And so I guess my question for you all, as well as you're doing these structures, is there a precision to the work that you see that's above and beyond a sort of standard conventional facade stone cutting, or is it exactly as you did before and just putting them together in different ways for structure?
I mean, we have, compared to concrete, we've got a small amount of knowledge. It's only 6,000 years that